I am Luis Alfonso Dañez, and I will be here in front of you to present you some problems involving analytical chemistry 2. I'll be here explaining you how I got the problem, how I got the answers, and I will present you some solutions in order how to get this. So, starting from problem 8-21. Potassium can be determined by flame emission spectrometry or flame photometry using a lithium internal standard. The following data were obtained for standard solutions of KCl and an unknown containing a constant, known amount of LiCl as the internal standard. All the intensities were corrected for background by subtracting the intensity of a blank. So if we're going to plot the data, so here's the table. So for this row, this is the concentration of potassium presented as ppm or parts per million. And here is the data for the intensity of potassium emission. And here is the intensity for the lithium emission. So let's move on for the questions. For part A, plot the K emission intensity versus the concentration of potassium and determine the linearity from the regression statistics. Letter B, plot the ratio of the K intensity to the lithium intensity versus the concentration of potassium and compare the resulting linearity to that in part A. Why does the internal standard improve linearity? And for part C, calculate the concentration of potassium in the unknown. So let us move to part A. So after plotting the data needed, so let us go back to the table. So what we'll be needing is the concentration of potassium and the intensity of potassium emission. So after using the both of the data and plotting it in the table, it goes like this. So since it was asked to determine its linearity using linear regression statistics, what I did was plot the table using plot the data, all of the data in an Excel and use the Linest formula. So calculations taken from Excel. So the Linus results can determine whether an equation is linear or not. So how do we determine this? So for Linus results, we take the data of the concentration of the potassium in ppm and the potassium emission, right? So after the Linus results, we obtain the slope, the standard deviation of the slope, the intercept, the standard deviation of the intercept, and the r-squared, which is the regression. And some of these are not necessary, but we are going to focus with the slope, the intercept, and the r-squared, which is the regression. After using these three data, let's go back to the table. We see that the equation is 5.6113x plus 12.647. So the 5.6113x is the slope, then 12.647 is the intercept. Now, why is there an r squared here? So the r squared determines whether the equation given was linear or not. So if the r squared is equal to 1 or close to 1, an example is 0.999, therefore it is linear. If it is not close to 1 or not close enough to 0.999, therefore it is not linear. So in this equation, since the value of r squared is 0.8603, this equation is not linear. So for part B, plot the ratio of the potassium intensity to the lithium intensity versus the concentration of potassium, and compare the resulting linearity to that in part A. Question: Why does the internal standard improve linearity? So first things first, what we're going to do is find the initial ratio, or the ratio of the K intensity to the Li intensity. So how do we do this? Using the table, we get the initial ratio by dividing the intensity of potassium emission over the intensity of lithium emission. So an example, we divide 10 by 10 in order to give an answer of 1. So an example, again, we divide 15.3 divided by 7.5 in order to get an answer of 2.04. So following the same solution or same formula, we get the value of the rest of the initial ratio. After that, we will now be plotting the concentration of potassium in ppm versus the data for the initial ratio. After plotting both of the data, we get this table. And for using the Linus results, we get the results. Slope is equal to 0.9422. The intercept is equal to 0.2536. The standard deviation of the slope 0.0147, the standard deviation for the intercept 0.1453, and the regression, which is equal to 0.999. Using the equation y is equal to mx plus b, the equation is equal to 0.9422x plus 0.2537, and the regression is 0.999. So um, with the regression value of 0.999, which is very close to 1, we can tell that this equation is linear. So, for the question, why does the linearity improve with internal standard? Here is the answer. Using internal standards improves linearity. Why do I say this? Because when applying for it, the ratio compensates for the systematic errors. When using the ratio, when we divide both of the values, it becomes nearer to uh, to the equation. You know, when using the ratio or dividing both of the values, it becomes more precise. It becomes closer and closer to the linear line. So that's why we can see that the regression is equal to 0.999, which becomes better than the previous regression for the intensity of potassium emission. So let us move on to part C. So calculate the concentration of potassium in the unknown. So if we recall, the concentration K is equal to X, while the initial ratio is equal to Y. Since the unknown is X, then the Y is given. Therefore, let us go back to the table. Since the concentration of K in ppm is unknown, then the initial ratio is given, which is equal to 5.1978. So what we are going to do is substitute the initial ratio, which is equal to the value of y. So by substituting y for 5.1978, we then get an equation of 5.1978 equals 0.9422x plus 0.2537. Using algebraic methods and transposing of values, we get 4.9441 equals 0.9422x. Then dividing both sides by 0.9422, we get 5.2472 equals x, then rounded to 5.2 ppm. So that is how we get the concentration of K in the unknown using the equation given in the table. Now, let's try this second problem. So for a second problem, generate an equation that relates the P-n ion to E cell for each of the cells in problem 17. So there's a note here. For Ag2SO3, the Ksp is equal to 1.5 times 10 to the negative 14. For Ag3PO4, the Ksp is equal to 1.3 times 10 to the negative 20. So this is a problem which is an example of potentiometry. So okay, let us start. For, since we are finding for the data in the previous question 2117, um, here are the answers for the question 21-17. So these are all shorthand notations. So the SCE, which is separated by the salt bridge, then the analyte solution, and the reference, the indicator, I mean. Since it is asking for the relationship of the P-n ion with the E cell, we can tell that there is an anion in the shorthand notation. So the anion has the the compound with the substance with the negative value on the superscript. So for the four shorthand notations, we get the I negative, which is the anion, the SCN negative, and every substance with the I negative on its superscript becomes the anion. So let's move on. So what we need to recall is the equation for the potential of the cell, which is equal to the E cell equals to the E indicator minus E reference plus E junction. For the E junction, we assume in this problem we assume that the E junction is equal to 0. So we don't mind that. So it becomes 0. Then the equation for finding the E indicator is equal to the reduction potential table value minus 0.0592 all over n, which is equal to the number of moles of the given, times the logarithm of 1 over Ksp. Now, we will be needing this for the future problems, and I will explain that later. Also, let us recall the standard electrode potentials. So, we will be needing this in solving for the given and for the required. So let us move on for part A. So for the I negative, which is the anion, we transform this to an equation. To a, then we can it we transform this equation which is given here. So AgI in solid is becomes Ag solid plus I negative. So first we find for the given. So for the given, the standard electrode potential of a silver iodide is negative 0.151 volts. So we got this from the table, from the previous table that I have shown you. So let's go back. Then the given is the SCE saturated equals 0.2444 volts. All of these are given from the these are given and these are fixed. The SCE saturated is we got that value from a table. So for the calculation, let us move on for the calculation. Using the formula E cell minus in the E cell minus E indicator minus E reference plus E junction. Then substituting the E indicator, which is the negative 0.151 volts, minus 0.0592 logarithm of the concentration of the I. Since it is not given, it's therefore a value, a variable. And then minus 0.244. The 0.244, it refers to the voltage for the SCE saturated. Then after that, we are going to simplify. So we can see that in order to find the p-value of something, we are going to take the negative log of it. So after taking the negative log of it, it becomes, and also simplifying the equation. So we uh, we add the negative 0.151 and the negative 0.244. So it is equal to negative 0.395 plus 0.0592 pi. So the pi was taken from the logarithm of the I. Therefore, using algebraic methods and transposing the values, we get the P of I is equal to E cell plus 0.395 all over 0.0592. Now, moving on to part B, since the anion is the thiocyanate or the SCN, we therefore transform this to the equation. So AgSCN solid yields Ag plus SCN negative. So the given is the SCE, the saturated SCE at 0.2444 volts and the KSP. Now, this is the time that we will be using the equation, which is the finding for the E indicator, which is the E standard potential electrode minus 0.0592 all over N times the logarithm of 1 over KSP. Then using this, using the equation and substituting it, we get 0.799 minus 0.0592 times the logarithm of 1 over its KSP. So since the KSP is equal to 1.1 times 10 to the negative 12, we substitute that for the denominator. Then after simplifying the equation, we get that the E indicator for the silver thiocyanate or the HSCN equal to 0.091 volts. Then after solving for the E indicator, we are now going to substitute for the E indicator of the SCN, AGSCN, to the equation. So E cell is equal to 0.091 volts minus 0.0592 logarithm of SCN minus 0.244. Then after simplifying and applying algebraic methods, we get negative 0.153 plus 0.0592 PSCN. Since we are finding for PSCN, we transpose it to the left, then using once again algebraic methods and simplifying, we get that the PSCN is equal to the E cell plus 0.153 all over 0.0592. Now moving on to the next part. So for C, now that is it is finding for the Ag3PO4, the PO4 negative, which is the anion, if you remember correctly. So we are going to transform that once again to an equation. So Ag3PO4 solid yields 3Ag plus PO4T negative. So the given, the SCE saturated, which is equal to 0.2444 volts, and the KSP, which is the equal to 1.3 times 10 to the negative 20. So we're going to recall again in order for formulating the KSP. Since the AG has a coefficient of 3, we transform that 3 into its power when using the KSP formulation. So that's why we can see that the AG has a power of 3. So let's move on. For the calculation, in determining the EAG3PO4, we use the value, the standard electrode potential of silver once again, because since it contains silver. So 0.799 minus 0.0592 all over 3. Why is it all over 3, if you ask? It is divided by 3 because if you recall that the formula is 0.0592 all over n, which is equal to the moles. We can see that the coefficient of the silver is 3, right? So the 3 becomes the n. So that's why it becomes 0.0592 all over 3. And then we multiply it to the logarithm of 1 over KSP, which the KSP equals 1.3 times 10 to the negative 20. After simplifying and using algebraic methods, we get to a value of 0.407 volts. Now that we have gotten the E indicator for the Ag3PO4, we substitute that once again to the equation. So 0.407 minus 0.0592 all over 3 logarithm of the PO4 3 negative minus 0.244. After again simplifying, we get 0.163 plus 0.0592 all over 3 times the PPO4. Since we are finding for the PPO4, that becomes the variable y. So we move it to the left. So PPO4 is equal to 3 times E cell minus 0.163 all over 0.0592. Now for the last part, that was a typographical error, so it was supposed to be D. So since we are finding for the relationship P and ion, the PSO3 negative, and to the E cell. So since the SO3 negative, we are going to transform that to Ag2SO3 solid that yields 2Ag plus SO3 2 negative. So once again, the given is the SCE saturated equals 0.2444 volts. Then the KSP, which is equal to 1.5 times 10 to the negative 14. So let's move on for the calculations. So once again, since the E indicator is not given, we are going to determine its value. So determining the E indicator for Ag2SO3. So once again, we're going to use the standard electrode potential for silver. So 0.799 minus 0.0592 all over 2. The n becomes 2 because the coefficient for the silver becomes 2. So that becomes the number of moles. So 0.0592 all over the number of moles, which is 2. So again, we're going to multiply that with the logarithm of 1 over 1.5 times 10 to the negative 14, which is the KSP. After simplifying and using algebraic methods, we get to an answer of 0.390 volts. After determining the value for the E indicator of Ag2SO3, we are going to substitute that for the first equation, right? Which is the E cell is equal to E indicator minus E reference plus E junction. Since the junction is 0, you won't be minding that. So substitute 0.390 for the E indicator. So 0.390 volts minus 0.0592 all over 2 once again, because the number of moles for the Ag was 2. So 0.0592 all over 2 times the logarithm of the SO3 2 negative minus 0.244 volts. After simplifying, we get 0.146 plus 0.0592 all over 2 times the PSO3. Once again, after simplifying and using algebraic methods, we get to the equation PSO3 equals 2 open parenthesis times the E cell minus 0.146 close parenthesis all over 0.0592. So thank you for listening, and if you have more questions or big concepts that you want to enlighten more, you can comment. You can comment below the comment box for more questions. So once again, this is Luis Alfonso Dañez, and thank you for listening and for imparting my knowledge about potentiometry and linear regression statistics. That is all, and thank you.